In this video, we're going to find volumes of solids, specifically solids of revolution, using the shell method. For each of these problems, we're going to use the shell method every time, but in the next video, we're going to work some problems where it'll be interesting. We'll be finding solids of revolution, but we're going to, based on the problem, we're going to make a decision about whether to use the shell method or the disc or washer method. So that'll be interesting. But for each of these problems, we're going to use the shell method. So the goal is we want to find the volume of a solid that's obtained by rotating the area contained within the given curves. And for these first three problems, we're going to be rotating about the y-axis. And then for the last three problems, we'll be rotating about the x-axis. So what's the volume of a solid created by rotating the area contained within these three curves? So here's y is equal to x cubed. Here's y is equal to 0, and here's x is equal to 1. So this area, we're going to rotate that about the y-axis. What's the volume of that solid? All right, so the shell method. For both the shell and the disc or washer method, in the plane here, we're going to have just a rectangle for both. But when you rotate that rectangle about the axis, so the y-axis, in one case you get a disc or a washer, in the other case you get the shell. So obviously here we're going to be getting the shell. So if you think about it, I can just think that, okay, we're going to be doing this. Because then when you rotate this about the y-axis, what do you get? You get that shell. Right? You see? Whereas if we were doing the disc or washer method, now if you rotate this about the y-axis, you get, a washer. See? Now, which method to use, that's something we're going to talk about in the next video. Okay, so our rectangles are going to look like this. And the delta independent variable is the thickness of the shell. So we're going to be breaking up the independent variable here is going to be the x-axis. And if we imagine if we draw a sample rectangle here, let's say this is the size of the interval width. What we do is we use the midpoints for the height of the rectangles. And for the shell method, you actually want you want to specify, like you don't choose left or right endpoints like we talked about for other methods. Here you actually want to use it's defined to be each element is defined to where it's not defined with an x star, an xi star, meaning for each you evaluate the function for the rectangle at any point within the interval width. It's actually defined to be the midpoint. And that's just because of the way the cylindrical shell volume is determined. You determine it using the radius at the midpoint of the thickness. So it's actually defined this way. But when it comes to the integral, when you take the limit as n goes to infinity, it doesn't matter anyway. Like you could choose the left endpoints and it wouldn't matter anyway, or the right endpoints, because as the limit goes to infinity, the delta x, everything all converges to, just the function evaluated at any point. But they still define it this way, because if you're doing an approximation with like n rectangles, like 50 rectangles, you want to use the midpoint for sure, because that's the definition of the volume of a cylindrical shell, is based on that midpoint radius. So, all right, so we're going to be integrating then. So this is the independent variable. We're going to be integrating from 0 to 1. So b is 1, a is 0. And the function is the height of the shell. So again, let me draw the shell here. So okay, the function is the height of the shell. Okay, but but we're what we want though is our function inside of the. So we're going to have an integral from A to B to get the volume, and we want the v of x. So, well, no, that's not right. This is kind of confusing because okay, what we want is okay. What is the volume of this of a cylindrical shell? It's you take the circumference of the the radius at the midpoint of the thickness. You take that's defined just as just r. So you get that circumference, then you multiply that times the height, and then you take the, if we'll call this delta, well, that's the thickness. We'll call that the thickness. Okay, the thickness is the dx. Okay, so the function here is everything else but the thickness. You see this 2 pi RH. So it's like that surface area of that mean, of that midpoint, you know, the circumference of the midpoint radius times the height. So that's surface area. That's what the function in the integral is. So I don't know what I'd call that, but okay, yeah. So what is h? H here is, let me remove this. So h is the height of this rectangle. Okay, so h is cube root of x. Well, okay, we need the 2 pi. Now let's put the h. Okay, so now what we need is the r. That's the only thing we need. Well, what's the r? It's, so we're revolving around the y-axis. It's this distance. What distance is that? That's just x. It's x midpoint, but as for an integral, as n goes to infinity, it's just x. And then d, and so that's 2 pi rh. Now the t is just the delta x. Okay, and we're going from 0 to 1. That's it. That's it. That's the volume of the you know, of the solid. So rotating this entire region about the y-axis. So okay, we've got 2 pi x to the 1/3 times x to the 1st. That's x to the 4/3. Okay, so we've got 2 pi, and then, all right, x to the 4/3 plus 1 is 7/3 divided by 7/3. Take this from 0 to 1. Okay, so this becomes 3/7. We can bring that out. So 6/7 pi. Okay, and then we've got x to the 7/3. Okay, so this is just 1 minus 0. So there you go. Okay, same problem. We're going to be revolving about the y-axis, the region contained by these curves here. So this is x is equal to 1. This is x is equal to 0. This is y is equal to 0. And then here is e to the minus x squared. And so the shell is going to be, well, we'll do dx again. And yeah, I guess since we're revolving about the y-axis, we'll always use x as the independent variable. That should always be the case. But so let's draw an element here. There's that. It's evaluated at the midpoint, like that. Okay, so we're integrating from 0 to 1. That's the independent variable x is equal to 0 to x is equal to 1. Okay, and what was it? It was the volume of the shell is 2 pi r h t. And so the function inside the integral is this here. And then the t is going to be taken up by the dx. So 2 pi, the r here is just x. The height is e to the minus x squared. The function evaluated at x, dx. There we go. Okay, we can take out the 2 pi. Okay, now this integral we can use, we haven't talked about any special techniques of integration, so I'm assuming we need to use substitution here, and that is going to be the case, because you can see that if you make u equal to minus x squared, then du, the differential du, is minus 2x dx. So let me do this, save some room. So du is minus 2x dx, and therefore, what is x dx? Minus 1/2 du is equal to x dx. Or we're here, yeah, see? X dx, that's what we're looking for. So now we can do the substitution, replace minus x squared with u, and x dx with minus 1/2 du. So the volume is equal to, well, okay, when x is equal to 0, u is equal to 0. When x is 0, when x is equal to 1, right, u is equal to minus 1. So we've updated the limits of integration, and now we've got what? E to the u, and then x dx is minus 1/2 du. So we take out the minus 1/2, and we've got minus pi, all right, 0 to minus 1, e to the u du. There we go. That's cleaned up. So this is minus pi and e to the u from 0 to minus 1. So minus pi, and you go e to the minus 1 minus e to the 0. So minus pi, well, we can do this. Let's just make it pi and then 1 minus 1 over e. And there you go. That is the volume. The volume of a solid that's obtained by rotating this area about the y-axis. Okay, same type of problem. We're gonna rotate about the y-axis again, the region contained by these two curves. So here's y is equal to x squared, and here is y is equal to 6x minus 2x squared. So, okay, the rectangle that we're going to be rotating is, let's draw a rectangle here. So evaluate it at the midpoint, so about there, and then evaluate the midpoint here. There's a rectangle. Okay, we're going to be rotating this, right? And then so the V is again 2 pi r h t. Okay, now we're going to be integrating from 0 to, it looks like 2 here, but let's verify that. So let's set these two equations equal to each other. X squared is equal to 6x minus 2x squared. Add 2x squared to both sides. You get 3x squared is equal to 6x. Okay, now you don't divide by x. That, you want to solve it by doing 3x squared minus 6x is equal to 0. Factor out a 3x, and you get x minus 2 is equal to 0. So x is equal to 0 and x is equal to 2. There you go. X is equal to 0 and x is equal to 2. If you had divided by x, you would have lost the x is equal to 0. So that's all algebra. We learn all that in algebra. So all right, so this is equal to 2. So we're integrating from a is equal to 0 to b is equal to 2 along the x-axis. All right, so the volume is, we go from 0 to 2. 2 pi r is just x again. It's not always just x. H is, okay, we're going to need more room here. So, okay. So 2 pi x, and then the height is what? The height is this blue curve, the x evaluated for this blue curve minus x evaluated at the red curve. So that's 6x minus 2x squared minus x squared. Okay, so there's 2 pi r, there's the height, and then dx. Okay. 2 pi x 6x minus 3x squared dx. Okay, we can take out a 2 pi, and we've got 6x squared minus 3x cubed dx. Okay, we can factor out a 3, and we get, so 3 times 2 is 6, so 6 pi 2x squared minus x cubed dx. Okay, so 6 pi 2/3 x cubed minus 1/4 x to the 4th, evaluated from 0 to 2. Okay, so 6 pi, and at 0, this is all 0, so we just need to plug in this evaluated at 2. So 2 cubed is 8. 8 times 2 is 16, so 16 divided by 3. 2 to the 4th again is 16. 16 divided by 4 is 4. All right, so we've got 6 pi 16/3 minus 3 over 3 times 4 is 12/3. 6 pi, and then you've got 4/3. Okay, so 8 pi. Yeah, there you go. That's the that's the volume. Okay, so now we're going to rotate the area contained between the given curves about the x-axis. So, okay, here's y is equal to 1. Here's y is equal to 3. Here's x is equal to 0. And here's xy is equal to 1. So that's y is equal to 1 over x. So we want to rotate this region here, this area here, about the x-axis. Okay, and so if you think about how do you get a shell rotating about the x-axis, it's going to be a horizontal rectangle. So, with the function, let me redraw that. The function will be evaluated at the midpoint. So like that. Okay, yeah, so you can see you rotate that about the x-axis, you get a shell. Okay, so let's set this up. Well, okay, well, we're going to be, the independent variable is going to be the y-axis, right? That's what our delta, the thickness of the shell is the delta independent variable. So, okay, so again, 2 pi r h t. We're integrating from y is equal to 1 to y is equal to 3. So y is equal to 1 to 3. 2 pi, what is r here? It's whatever the y coordinate is. Well, okay, let me make sure that's right. Yeah, because we're rotating it about the y-axis. If we were rotating it about the, y is equal to 1, it'd be a little bit different, because we would the y coordinate, like that, we're trying to find r here. So if we were rotating it about y is equal to 1, then this would be the r. You see? But in this case, it's just we're rotating about the origin or the x-axis. So the r here is just whatever the y coordinate is. So you just put y. Now the height is this red function evaluated at, but we want to get the x coordinate. So here, what is the x coordinate? It's 1 divided by y. So if we take this y and we say 1 divided by whatever this y is. If we say, we say 1 divided by whatever this y value is, whatever this value is, this y value, we take 1 divided by that, that's this distance. And that's what we're looking for, is for the height. So we say 1 divided by y. All right, now the thickness, dy. There we go. Let me bring the 2 pi out. These cancel, so we're just left with 2 pi. And this is just going to be 3 minus 1. Four pi. Okay, we want to rotate the area contained within these 3 curves about the x-axis. So let's see. Here's x is equal to 0. Here's y is equal to 8. And here's x to the 3/2. So if we draw a rectangle, there we go. It's evaluated. The function's evaluated at the midpoint. So if we're going to rotate elements like this about the x-axis, okay? And so we're going to be integrating from 0 to 8. 2 pi, what is the r here? R is just y again, y. And then what is the height? It's just, so, okay, we need to, let's do this. Let's get the, okay, so we need to solve for x as a function of y, because we want to input this y and get whatever this horizontal length is. So x to the 3/2 is equal to y. That's the equation for this curve, right? You plug in an x, you get a y. Plug in an x, you get the y. But we want to solve for x as a function of y. So we raise this to the 2/3 power, and that's a cube root there, so we don't need to put any pluses or minuses. And so we get x is equal to y to the 2/3. Okay, so now let's come back to the formula. We're going from 0 to 8, 2 pi y. Now, y to the 2/3, right? If we weren't rotating about x is equal to 0, we'd have to adjust this a bit. But we're just not, for rotating about x equal to 0, we're just, the height and the radius are just functions of, the y coordinate. The y coordinate to the 2/3 power is this horizontal distance. Okay, and then dy. So we've got 0 to 8. Y to the first times y to the 2/3 is y to the 5/2. Okay. So y to the 5/2 plus 1 is y to the 7/2 divided by 7/2, evaluated from 0 to 8. So we take out this 2/7, and we're left with 4/7 pi y to the 7/2 evaluated from 0 to 8. So 4/7 pi, and then just 8 to the 7th half, 8 to the 7 halves. So 8 to the 7 halves. So let's plug this into our calculator. 8 to the 7 halves times 4/7. Okay, wait. I don't know what I was thinking here. Y to the first times y to the 2/3 is y to the 5/3. Okay, so then you get 5/3 plus 1 is 8/3 divided by, that would, so then you'd have, this would be 8/3. So you bring out 3/8, and that results in 6/8, which is 3/4. Okay, this is 8/3. So this is 3/4, 8 to the 8/3. Okay. So 8 to the 8/3 times 3/4. 192. So 192 pi. Okay, we want to rotate this about the x-axis. So here's x is equal to 2, and here's x is equal to 1 plus y minus 2 squared. And so you can see that we're going to have, this would be a rectangle, and we're going to rotate that about the x-axis. So we've got 2 pi RHT. And okay, so we're going to be doing dy, because this is the delta y. And so the limits of integration look like they're going to be from here to here. But let's solve for what these y values are. So we set these two equations equal and solve for y. So plus or minus. So you've got y minus 2 is equal to plus or minus 1. So y is equal to 2 plus or minus 1. So y is equal to 1 and y is equal to 3. And that is correct. Here's 1 and here's 3. Okay. So we're integrating from a is equal to 1, y is equal to 1, to y is equal to 3. Now the height is going to be what? It's going to be 2 minus this 1 plus y minus 2 squared. So, all right. The volume is equal to, we're going from 1 to 3, 2 pi. The r is just going to be, again, just the y coordinate, y. And then the height is 2 minus this 2, okay, yeah, 2 minus this x coordinate, which is this 1 plus 2 minus 1 plus y minus 2 squared dy. Okay, so 2 pi y Then we've got 2 minus 1 plus y squared minus 4y plus 4 dy. All right. 2 pi y, and then we've got 2 minus 1 minus y squared plus 4y minus 4 dy. Okay. So we've got 2 minus 1 is 1. 1 minus 4 is minus 3. So 4y minus 3 minus y squared dy. Okay, so if we take out the 2 pi, we've got what? 4y squared minus 3y minus y cubed dy. So you got, okay, 4/3 y cubed minus 3/2 y squared minus 1/4 y to the 4th. Evaluated from 1 to 3. Okay, so let's see. 3, plugging in 3, it's 3 cubed. This cancels, so you've got 3 squared times 4. 9 times 4 is 36. All right, 3 squared is 9. 9 times 3 is 27, so 27 divided by 2. 3 to the 4th is 81, so 81 divided by 4. Minus, plugging in 1, you've got 4/3 minus 3/2 minus 1/4. Let's just use our calculator for this. So 36 minus 27 over 2 minus 81 over 4. 9 over 4. Minus, so 4/3 minus 3/2 minus 1/4 minus 5/12. Okay. 9/4 plus 5/12. 8/3. 8/3 times 2 pi is 16/3 pi. And there we go. So now in the next video, we're going to find the volumes of solids of revolution, but it's going to be interesting because we're going to analyze each problem and decide whether or not to use the shell method like we did here, or the disk and washer method, which was based on the traditional method of volume integration with the right cylinders.